All right. Hello, everyone, and thank you for joining in for this live session. Very warm welcome to everyone who is joining in for this live session. All right. Good morning, good evening, good afternoon to everyone present here. And today we are here for the third live session with our esteemed panel of judges. And now we have none other than Mr. Adheesh Boratkar, which I'd like to invite him onto the screen. All right. So with us we have Mr. Adheesh Boratkar, who would be your judge in the satellites category, and you can go ahead and interact with him now, and also you can go ahead and interact with him in the grand finale as well. So Mr. Adish Voratkar is a hardware engineer at Kepler Communications with a master's of applied sciences degrees in electrical and computer engineering from the University of Toronto. He has prior experience working as an avionics engineer at Axiom Research Labs and as a system engineer at the Parikshit Student Satellites team. He has also co-authored multiple research papers in the field of aerospace and aeronautics, and that is Mr. Adish Voratkar right in front of you. Well, thank you so much for agreeing for this live session. I'm pretty sure that everyone would be excited to interact with you and to know more about you.
Oh, thank you so much, Shatik. I'm very happy to be here.
All right, so thank you so much. And well, I see that we have got a number of audience as well, and thank you so much for tuning in. So, Mr. Adish Varatkar, uh, you are currently doing a lot, and you're currently working in Kepler, but there is something which our audience would love to know and would love to know about every judge, and that is, do you love space from your childhood? And how did you get your first inspiration to pursue the same? Or, in other words, what made you or how did you enter this space industry?
Right. Honestly, like growing up, I didn't particularly like space as such. I mean, I always was fascinated by it, but I was more curious as to understand how things work, and ended up breaking things, and was for the most part not able to put them back together. Uh, but along the way, opportunities came up, and in fact, the earliest instance that I can think of, where anything like I was exposed to, or like I was thinking about doing something for space, was in 2007, when IAC, or the International Astronautical Congress, happened in India. And that time, ISRO had made an announcement saying, if Indian students are able to design and build a satellite, they would launch it for free. So my father told me about this and asked me to think about building a satellite. And at that point, it just seemed such a unreasonable ask, and like such a massively complex thing, that how could students ever do it. But when I joined engineering in Manipal, uh, there was a student team doing exactly that. So I got involved with them, and I think that's how I really got introduced to the space industry.
Well. So that not so impossible task was actually achievable, and we have achieved it as well. And that brings us to, or that makes me wonder that exactly that your student satellite team at Manipal, which is named as Parikshit. So can you just go ahead and or tell us about your experience working in the same? What was your role? What did you guys do exactly in Parikshit?
Yeah, so Parikshit was a student team. We were about 40 to 50 students, depending on the exact time. And it was We were trying to develop a 2U class nano satellite. Uh, so a 10 by 10 by 20 centimeter long CubeSat, which weighed like less than 5 kg. And it was a completely undergraduate student run project. I have a few slides later on. I can talk more about what we did in Parikshit, and how it went.
All right, so we'll come back to, or we'll loop back to Parikshit later on. So I
Yeah.
think first we'd like to cover up that what or can you just go over about and tell us more about your Kepler communications? What are you doing and what are your plans in the future? And I think you have a few slides which you'd like to present, right?
Yes.
All right. So I think, yep, there you go. You are now all set up.
Okay. Thanks. So yeah, I joined Kepler like about 2.5 years ago as a hardware design engineer, and I design uh, like both electronics hardware for both onboard systems as well as systems that are used on ground. A little bit about Kepler. Today, we are the largest satellite operator in Canada, like in terms of number of satellites. So we have 19 operational satellites in the low Earth orbit, and our satellites are communication satellites. So we have Ku band radios, and we do point to point data transfer at really high speeds. Uh, we have a facility where we do the assembly integration testing and of these satellites, so we can produce about 10 satellites in a month, and that's the hardest we have had to push our limits so far. We've also demonstrated inter-satellite link on two of our recent satellites, so you can transfer data from one satellite to the other rather than just transferring data between Earth and space. About 120 people and growing. We have ground stations in Canada, New Zealand, Norway, and a very strong regulatory position. With we're hoping to expand to a constellation of 140 satellites and offer services in Ku band, Ka band, and S band. These are all like different data rates serving to different applications. So that's what we are doing right now. What we have been doing so far, but our big dream, so to say, is to build internet for space, and I can talk about that a little bit in the next slides. These, by the way, are our current generation of satellites in the lab during the AIT phase. So these are 6U satellites, so 10 by 30 by 20 centimeter in dimensions. So our core belief is that if humanity needs to be like a spacefaring civilization, we need to have connectivity. And right now, the sad part is that most assets in space are only be like they are not in contact with the ground throughout. So you have a ground station and you have a satellite. You have to wait for that satellite to be visible over that ground station to talk with it. And in the low Earth orbit, where like a typical orbit lasts 90 minutes, you get a pass that is over a ground station, which is usable for about 10 minutes, let's say, and you get two such passes in a day, or you might get a couple more partial passes. But needless to say, like about 70% of the time, uh, you are not in contact with the asset that you have in space. And what we propose to do and what we are working towards is to change this. So we are going to launch our own network of satellites which will act like routers. So we'll have the capability to pass on data from one satellite to the other, and then as long as you're connected to any one of our satellites, you can access your space asset, you can communicate with it, you can get data from it almost in real time over your ground station, because it will just travel through our network and reach you. So that is what Kepler is trying to build, and that is what we are calling, providing internet in space, and first around the Earth, and then even beyond. Our like product roadmap looks like this. So uh, we want to offer like high data rate services in the Ku band, uh, low data rate services in the S band. So this would be mostly for doing command and control of your satellite, whereas the Ku band would be to actually get payload data from your satellite. And right now, we plan the our network backhaul to be over optical, but going forward, depending on how the demand is, we might even uh, connect with customer satellites directly over optical. So that's like the big plan of what Kepler intends to do. And right now we are just in the pathfinding stages for this. So we are building the first two satellites that will form this network, but we have really ambitious plans, and uh, looking forward to scaling this up in the years to come.
Well,
So I can
well,
take a
that
pause there,
is.
Satek, for now.
Yeah, well, that was a lot about Kepler and what Kepler is doing, and what what Kepler currently is doing is a lot, or is it is one of our or most of our favorite topics, because internet in space is something which we really look forward to, and Kepler is going forward with it. That is first of all tremendous, and that is really fabulous what they are trying to do. And you've explained, or you've said there's about, I think, ether routes. I think, could you just go over and tell me what exactly is an ether route?
Oh,
Ether
so yeah,
router. Ether router.
our next generation of satellites will be called Ether. So that would be that's the name of our satellite. Yeah, so
Okay.
the Ether would be the name of the router, and yeah,
So, as in, like, the main router, the name of the router is simply an ether router, right?
yeah, like name of the router, name of the satellite is Ether, or so I hope. Uh, because
All right.
we've had like a little bit going back and forth on the terminology, trying to make it less confusing, but in the process, uh, uh, yeah. So yeah, Ether is going to be the name for our satellites. Yeah, and the
All right.
services are going to be in the Ku band, S band, but our satellites for this constellation would be called Ether satellites. So it will be
Is
like
that
Ether one, Ether two, Ether three, so on up to Ether 20 or Ether 120, depending on at what point you're looking at this network.
all right? So, looking forward to ether. Not 120, maybe more than ether 120 as well. So we have got a question related to that, and that is, do you plan to provide internet on Moon and Mars as well?
Well, we want to provide connectivity uh, across space. So eventually, definitely. But first
Well,
around the Earth, and there's a long way to reach the Moon and Mars. But yeah,
we're looking forward to that as well, where we can also use the internet on Moon,
and
and
again,
maybe
to clarify, like what we
uh,
are trying to do is not provide the internet as we know on Earth in
uh-huh.
space, but like create a communications network for space assets. So uh, yeah,
Kind of like how internet is established on Earth, we want to simply take it up to space. And how internet is, there is the server where all, or internet is basically an exchange of information, right? That is what basically
exactly.
it
Yes.
basically stands for.
Right. So we want to connect assets in space so that they are not lonely, and uh, you can have like bidirectional flow of information all the time.
All right. So, well, that is something fabulous about how internet in space, and that is the next generation which we are looking forward to. That would be for all about Kepler. And now, moving forward, I think which we talked about in the very beginning, that is about your student satellite team named Parikshit. So let me just look back to that question, and that is that. What was your, or how was your experience working in Parikshit, and what was your role? Could you just go about telling a little in detail about what do you guys do, how did you achieve it, and a little detail about that as well?
For sure, for sure. So like when you asked me to give a talk, I was thinking, what to talk about, and then I said to myself that what do I do? I build satellites. So let me talk about how to build uh, uh,
Satellite.
how to build satellites, and try to demystify that a little bit as much as possible. So like I'll probably go back and like uh, to my presentation and try to see how that flow goes. So as I said, like I first heard about this fact that students can build satellites in 2007 when my father told me about this announcement ISRO made at the ISE in Hyderabad. Then I joined Manipal, and this was the group that I was working with, Parikshit. We were like an undergrad team of about 40 to 50 people. This is from one of our college yearbooks. And no, we always don't look so serious and in black and white. So this is a color picture from us, and this was from a recruiting event. So like once a year we would hold this talk and like try to get more people from the university to join our team. And I had a lot of fun along the way. Got to work in clean room with like some really cutting edge technology. Got to visit ISRO, present our work to them, get feedback from the scientists there, and also got to be on a zero gravity flight, like a parabolic flight. So, but back to what Parikshit was, it was a, as I mentioned initially, a 2U CubeSat. So you have a 10 by 10 by 20 centimeter long satellite. It's really small. And initially, I started in the payload subsystem and ended up being a part of the systems engineering group towards the end. And I dug up this document from our preliminary design report, and I see that in 2013 I had just been added to the group and was doing minor things like editing and formatting. But in order to explain how to build a satellite, I thought it is first important to know why we are building a satellite, and it's important to have that clarity of thought, because otherwise the task just seems daunting and such a complex system. You don't know how to go about breaking it down and conquering it one by one. So in Manipal, we were a student team. Our main objective was to gain hands-on experience and learn about this technology. So we set that down as our first mission objective, uh, to give hands-on experience to build a satellite and make it functional. The second objective was to launch this satellite and communicate with it using our own uh, ground segment. The third objective was to operate a scientific payload or a technology demonstration payload on board. And from this third objective, we derived two science objectives along the way. So we wanted to do thermal imaging of the Indian subcontinent. And of particular interest to us at that time was this concept of urban heat islands, where uh, you know uh, cities heat up more than their rural surroundings, and even at night, as the rural surroundings cool down, cities don't, because of all the concrete that is trapping the heat. And then our second science objective was to deorbit the satellite at the end of its mission, so that it doesn't contribute to space debris. And for this, we had a partner in Sabre Astronautics who provided us with an electrodynamic tether mechanism, and I can talk more about it later. Uh, but what I basically thought was, I could talk about the space environment, the launch environment, and then about how, uh, based on the challenges that this environment poses, uh, satellites need to combat these, and how they're typically met in forms of subsystems. And spend a little bit time talking about that, and then talk about how traditional or old school space is different from what companies like Kepler and many others are doing right now in the new space ecosystem. And then towards the end, since electronics for space is my specialization, talk a little bit about that, answer some questions. So does that seem all right, Swatik?
Well, yes, definitely, and that is about, and you have explained a bit about Parikshit as well. So there are a few questions about Parikshit also, and that is, when you were going forward with the satellite and creating a satellite, did you have the ground station access? And if yes, how did you downlink and uplink the data?
Right. So, yes, we set up our own ground station. So, we had a VHF, UHF station set up in Manipal.
Mhm.
And initially, we took help from, looking at other student satellites, how they had done it. And also, we had a local ham club there who were
Huh.
helpful. Ham is like amateur radio. Uh,
Okay, okay, yeah.
yeah.
Uh,
So we had help from them, and we did, while I was there, like, although I was not involved in the setup of the ground station, there was a whole different team doing it. But it's always very exciting, so I you know was always curious and kept following up with them. And I was there when they received some data from other student satellites. So we received the beacons, which is basically a Morse code signal that transmits the identifier of the satellite and some basic health parameters. So we received data from other satellites, and I also remember we were tracking the Mars orbiter mission for its last orbit around the Earth before it took off towards Mars. So we didn't have any equipment to receive signals from it, but we had a sort of an antenna and an antenna pointing mechanism that was geared to track satellites across the horizon. So we just tracked the Mars orbiter mission, and that was an incredible feeling.
Okay, that is indeed, I mean, that's awesome. And I believe I saw one picture about you, I think floating in space or something. Is it, or was it in ISS, or was it in a microgravity situation?
No, so that was a parabolic flight. So NASA has
Okay.
this thing called the Flight Opportunities Program, and our uh, like collaborator for the tether experiment, this company called Sabre Astronautics, they are based in Australia. They had applied to test the deployment of their mechanism in microgravity. And since I happened to be the person working on that part of our satellite at that point, I was in the payload subsystem. They invited one person from Manipal to join them for the test, and I was chosen to be the representative from Parikshit. So like these flights happened in Houston. I got to be on three microgravity on three reduced gravity parabolic flights.
Okay, well, that is indeed awesome. I mean, that is only word which I can come up with. That is indeed awesome about how you're going forward with. So I think you can maybe proceed with the presentation. I think that is that those are a few things from my end. I think you can proceed with the presentation again.
Right. So when, as a student group in Manipal, we first thought of building this satellite. We didn't know much. We had access to uh, scientists at ISRO for clarifying things from time to time, but it wasn't like we could just call them up, or you know uh, it would be like once in 2 months visit them with prior appointments, and like we had to show a lot of homework. So we started googling as to what does it even take to build a satellite, and what is the environment like. And these are some of the things I learned then, and they are like even useful today. So one of the biggest challenges in space is vacuum. So you have really low pressure there, to the order of 10 to the power minus 6 and 10 to the power minus 9 torr. And a torr is like roughly 1 by 7/60th of normal atmospheric pressure. So pressure there is really low. And you might wonder, how does that matter? Because these are satellites, they're not living beings, they don't have to breathe. uh, so what is the problem with having low pressure? Well, materials tend to outgas. That is, they release volatile materials from within when they are in extremely low pressure, and these materials can then get deposited on other surfaces. And if you have any sensors, any optics, they can contaminate them, and uh, impede their proper functioning. So you want to make sure that any material you use doesn't outgas in vacuum. And the way this is typically characterized is by total mass loss. So you take the material, weigh it, put it in a vacuum chamber, and once it's done outgassing, you weigh it again. The other parameter that is used is the collective volatile condensable material. So you have a plate that is kept cold, and once things outgas, they go and deposit on this plate, and then you analyze how much depositions you've had. And there are limits for both these total mass loss as well as the collected volatile condensable material that is like permissible for a particular mission, that you have to keep in mind while selecting materials. So that's one of the challenges, that is vacuum. The next challenge is temperature. So when you are in direct line of sight of the sun, things can be as hot as 120 degrees Celsius. And when you are in the eclipse region, which is when you are in Earth's shadow and you have no visibility of the sun, things can get really cold, all the way to minus 120. And if you have materials that have like different coefficients of thermal expansion that are very close together, they might one might want to expand more than the other, one might want to contract more than the other, and that could lead to uh, stresses and strains being developed. So you have to be careful while selecting components as well. Like you need something, at least something that goes on the outside that survives this, and you want to make sure that your electronics never see these temperatures. So you want to be able to heat them in the cold and insulate them and like shield them from the heat during the sunlit parts of the orbit. Some other challenges are like UV radiation, plasma, atomic oxygen. All of these lead to uh, like more of surface level degradation. And honestly, I'm not an expert on the mechanical side of things, so I'll not speak too much about them for now. And I'll go to radiation, ionizing radiation. This is like the radiation we are all scared of. And electronics as well on board satellites need to be uh, protected from radiation. And there are two major kinds of radiation effects. Some effects that uh, accumulate over the lifetime of your device. So this is the total ionizing dose that the device accumulates. So if you have it there for 1 year, it will be something, and then if you have it for 2 years, it will accumulate more of that, and that leads to slow degradation in performance. And there are other effects which are known as single event effects. So these happen immediately when a charged particle deposits a particular charge at a specific location. So this is like energy being deposited, and like electronics at the end of the day, you can think of them as switches. And like whether a switch is on or off will represent if it's a 0 or a 1 logically. And these switches are typically controlled by MOSFETs. And uh, uh, what it takes to turn a MOSFET on or off is some charge at its gate. And if you have a charged particle that deposits that charge, sufficient charge, then you can have that switch flip its state from on to off, off to on. And that could corrupt your memory. It could like fire a thruster, or do many things that you wouldn't expect your satellite to be doing, because it's it's like a pseudo command that it receives. So that's the bigger problem for missions in the low Earth orbit that are not for designed for 15 years or so. The other environmental considerations are during launch. So when you're on the rocket going up, you may experience up to 11G in like random vibration and shock. And you need to design your structure to be strong enough to withstand that. When you're inside a launch vehicle and you're not the primary customer, the primary satellite safety is most important. So when you're a smaller satellite, they will typically ask you to be completely powered off, be completely off communications until you're ejected from the rocket. So you have to design your satellite that way. And you have to also design for transportation and uncertainties. So if you have to sit on the launch pad for a couple months due to bad weather or any other eventualities, your satellite needs to be able to do that. And apart from the launch loads, your loads experienced in transport also it needs to sustain. And this is not as trivial as it seems. Like you have to be actually analyze your parts and design them such that they survive transport. And then the last part is serviceability. Once you've launched, unless you're the Hubble Space Telescope, there is not much chance to really service your satellite. So your system needs to be very, very robust and highly reliable. So I think this concludes some of the challenges, in designing something for space. And next, I would like to talk about what satellites, like how satellites are built to overcome these challenges. So I'd like to take the example of Parikshit, which was the student satellite, and this is an exploded view of it. And I'd like to point out this mainframe here, which is the structure. So we had this big like massive challenge of wanting to design a satellite, and then through this slide I'll try to explain how we broke it down into more manageable chunks. So we had a team of mechanical engineering students who were doing who were designing the structure, analyzing it to make sure it's strong enough to, sustain the launch and hold the payload, this camera, for instance. So we had a team that looked after structures, thermals, and mechanisms. So now you have a strong structure in space at, let's say, 700 kilometers, orbiting the Earth at 7.5 kilometers per second, which is much, much faster than a bullet. But you can't do much unless you generate power. So we had a group of students in the electrical power subsystem whose job it was to size the solar panels, design the proper electronic circuitry to harvest that power from the solar panels, store it in the batteries for use during eclipse, and condition it to the right voltages so that the electronics on the satellite get exactly what they're expecting. Once you have a stable structure that is generating power, you want to point that structure to Earth. Let's say you want to image, let's say you want to click a picture over Toronto, and so you want to point at Toronto and not at Vancouver or the moon, let's say. So we had a we had a subsystem called ADCS that stands for Attitude, Determination, and Control. Attitude is your orientation of the satellite. So it was their job to know where exactly the satellite is pointing and figure out how off it is from where it should be pointing, and then provide inputs to make sure that offset is corrected for. This team, when I worked at Team Indus, since it was a lunar mission, was known as Guidance, Navigation, and Control, because their job was not just to point the satellite around the Earth, but also take it from Earth to the moon and execute a controlled descent. At Kepler, we call it AOCS because we have a thruster for orbit keeping, so it's attitude and orbit uh, control systems, I believe. So some of the sensors that they use are like sun sensors. So this is like we have like photodiodes mounted on each side of the satellite, from which we're able to estimate the angle that the satellite is making with the sun. We also had a GPS on board, which would give you your exact location. But due to power constraints, we couldn't use that GPS all the time. So we would use it only twice uh, in orbit, or twice in orbit, or twice in a day. I don't quite remember anymore. It's been a while. But we also had magnetometers, which gave a 3-axis reading of the magnetic field. And then there is a database called the IGRF, or the International Geomagnetic Field Reference. So you can compare the magnetic field that you are sensing and try to determine where around the Earth you would be if you are seeing those measurements. And so this is the determination part. Then to control it, we had magnetorquers. So these are electromagnets that you power on only selectively when you want to, and create a magnetic field there. And that magnetic field then interacts with the Earth's magnetic field. And when those two magnetic fields interact, that is what gives the, changes the orientation of the satellite. Uh, Later on, they moved to add reaction wheels, which are yet another mechanism to control satellites. Uh, so now we have a structure that is generating power and that is pointing towards the Earth. The next thing to do would be to communicate, to follow up with the satellite, whether it's doing okay, or to command it to click pictures somewhere. So we had the comms communication subsystem for that. And once you have all of this, you definitely need the payload, which is the reason why the satellite has been launched. So it's a very relative term. For a rocket, the whole satellite is a payload. For the satellite, the scientific instrument, or uh, the commercial instrument, or whatever is, like the reason for launching that satellite, is the payload. So for Kepler, our radios are our payloads. For Parikshit, the thermal imaging camera and the electrodynamic tether were its payloads. So you have a separate team that tries to work only on the payload, trying to make sure that that camera is, survives the satellite and you're able to extract data from it. To enable all of this, you need like a computing infrastructure there. So that is what an OBC, onboard computer, or an onboard data handling subsystems job would be. And then you have another set of people who look at planning this mission. Like, how often do we want to click images? how frequently do we want to downlink that data? Are we able to do that in one pass itself? Because you have very limited times over ground stations. So that becomes a big problem for Earth observation satellites. Sometimes you click images, and for the next many passes, you just spend downlinking them in parts. So you have people to plan the mission and operate the satellite. And when you have multiple satellites being mass produced, you have a dedicated team for the assembly, integration, and testing of them. And then, of course, while all these different teams are doing very specific things, you have the systems engineering group that has the big picture view, that makes sure that uh, all of these systems, subsystems, are going to be compatible with each other, and they will fit in together and fulfill all the requirements that we had at the high level for the mission. So this is a breakdown of how a typical satellite team or a satellite company is broken up as. Just for fun, I have a video of one of our antenna deployment tests from Parikshit. So let me see if I can actually get to uh, playing this video. So how this happens is, I was talking about mechanisms. So when you are in the rocket, you want to have a very small footprint. So our antennas were wound around this one face of the satellite, and they were tied together by a fishing line. And that fishing wire of sorts went over a resistor that would get heated and burn it after deployment, which would release these antennas. This is a quick video of that happening. So it's a old video. I'm sure after I left, Parikshit fine tuned this, but these are like two antennas that we had, one for the beacon transmitting the health and receiving telecommands, and the other for much higher data rate antenna for transmit for getting the payload data from our satellite. Similarly, another thing from Parikshit was these separation switches. So when you're inside the launch vehicle, you want to cut off power to the whole satellite. So these micro switches from Honeywell are what we had, and these rods would actuate them. And this is a test where uh, they'd be pressed when they are in the launch vehicle inside the deployer, and once they're out, that spring would push that switch out. And now uh, we have a colleague of mine looking at it with a multimeter. So when it's relaxed, it's like conducting, and as you press it, it would open that circuit and cut power to the whole satellite. So now it's conducting, and that's open circuit. Yeah, that's as much as I had to talk about Parikshit. Then I have this picture from my time at Team Indus. This was the lander, prototype of the lander that we were developing. And I'd like to segue into how old space and new space differ, and that is like what I have the next few slides for. But I'll break in between to see if Sautik has any questions. Are we doing okay on time, or all of those things?
Yeah, definitely. And so far, I'm enjoying the session, and so are our audience. Well, they do have a few questions as well, and that is, uh, Shant is asking, all this is exclusive to aeronautics and electronics. Can other branches, guys, join in the satellite design and communications module?
Absolutely. So what you need to realize is, to make any really usable product, you need all different specializations and skills. So like I was talking about the subsystems, so you had mechanical engineers doing the structures, you had electrical engineers doing power, you had computer engineers doing the onboard computer, you had uh, some, in some sense, you would have scientists doing the payload at many of these space agencies, or you would have like commercial people telling you how your payload should be designed so that they are able to sell it to customers. So to actually make a satellite, you need a lot of different skills, and as long as you can acquire any one of these skills, you can join a space company. And this is true for not just satellites, but even for cars, or like any usable product. It requires a whole lot of different skill sets to come together and collaborate to build this. So uh, like for instance, my all my education has been in electronics and electrical engineering. So my bachelor's was in electronics and communication engineering. My master's degree was in electrical engineering, and all my life I've worked on aerospace related projects. Although I don't have like any formal training in aerospace as such, but I have a skill set that is electronics design, which is very much required in aerospace. So that's what I'm leveraging to be here. So you can just find uh, and improve one of those skills that are required in building a satellite, and you can definitely be there.
All right, so Prashant, it's open for everyone and for all the branches. You can definitely go ahead and jump into that. And next, we have a question from VMSDM, which I'll like Mr. Adhish to answer. He's asking, so can we make make one of these satellites on our own?
uh, Absolutely, why not? Uh, there are competitions that happen that do satellite design on a conceptual level. There are also CanSat competitions where you design a transmitter uh, that fits inside a soda can volume, and then you launch it through a hot air balloon or something like that, and like receive data from it. So on a smaller scale, there's a lot of things you can do just on your own as well. But when you want to build something as complex as a satellite and want it to be useful, then I would think you need to go out there and collaborate with other like-minded people and put a team together. uh, it's really amazing what uh, we can achieve when we have like the right company and equally motivated people to work with.
Exactly, and with that exact objective, we have brought to you the Space Science Challenge, where you can go ahead and participate them, or you can go ahead and create your own team and participate with them as well. And I think, yeah, this is you have told about your team Indus, so you can maybe move forward with the same and give us a little insight or about how was your experience working with Team Indus, which was one of the finalist teams in the Google Lunar X Prize.
Right. uh, Yeah, so I was fresh out of college. I had just finished my bachelor's and didn't want one of those typical IT jobs. So I went out looking, and I had seen some people from Team Indus at a conference organized. That happened that was organized in Bangalore, and that is where for the first time I also met Narayan Prasad, who's the one of the other judges, and I think he'll have a session tomorrow for the first time. So I was a student still in my final year, and I saw these people. They were participating in the Google Lunar X Prize, which was an audacious challenge. So what the Google Lunar X Prize was an open contest for anyone to land on the moon, move for 500 meters, and send back HD video. And Google had a huge Google was sponsoring like a huge kitty of money uh, for anyone who was able to do this. And the X Prize Foundation was conducting this challenge. And X Prize Foundation's beliefs are to do radical change through incentivized competitions. So like the Ansari X Prize brought about the first suborbital flight, if I am not mistaken. And Google Lunar Express was the next most audacious thing. And here was a team which had uh, retired ISRO scientists on board working full time, and very young engineers like me. And we got to work under their direct supervision. So these are scientists who have designed, all their life satellites at ISRO. So we had the mission director for Chandrayaan, for instance, working with us. And these people who have designed like satellites for geostationary orbits that last 15, 20 years, they were guiding us on how to build this our own lander to the moon. So it was an incredible experience learning from them, uh, and also getting to know about the various challenges that are involved in designing things for the moon. So the moon gets hot when it gets hot, and it gets super cold when it gets cold. And like a day on the moon lasts 14 Earth days, and so does a night. And surviving the night is almost impossible unless you have like a nuclear power source on board. And the lunar regolith is charged like that, the soil. So got to learn a lot at Team Indus, and also hone my This is when I first specialized, like moved away from systems engineering at Parikshit and payload before that into actually designing hardware. So I was doing the schematics for one of the main avionics cards. I was doing like a lot of electronics for their propulsion control as well. And yeah, it was an incredible experience.
All right. Well, thank you so much for your experience in Team Indus. So next we have got limited. We have got few questions which I like to sum up with another question, and that is, yep. So that is ISRO has recently announced that it will launch 75 student satellites next year. What do you think about this initiative? Do you think it will help in developing a new generation of workforce that can help to fill up the gap of space engineering in India?
Absolutely. I am really looking forward to this. And they have announced that they want to do this, and they have announced even partners who can actually help universities achieve this. So there's a trade-off, like when we were there was no such established players in India. We had to go about doing everything on our own, and we spent a lot of time uh, you know uh, reinventing the wheel, but also learned quite a lot. So now with these 75 satellites, what my understanding is, the platform has been standardized, and the payloads are going to be for the universities to develop. So I think the scope is much more limited. There is a dedicated industry body that is going to guide the students, because that's another thing. Like typically, professors do not have that much experience in designing satellites. I mean, anyone outside of ISRO didn't have experience doing satellites in India back then. So there are like so it's really good. I think more people will get exposed, and this will really help train like human resource as well for our space startups, which are like doing just amazingly well. If you look at how many of them have been funded and how many of them have been doing things, launching things, uh, I, I I am really looking forward to these satellites.
Well, audience, now you have a new objective in mind and you know what you need to aim forward next. So go ahead and develop your own satellite. That is what I'll say. And okay, so next coming forward a little into the electronic side, and that is, well, recently there's been a semiconductor chip shortage. So how's the space industry reacting to the global shortage of semiconductor chips?
Yeah, so on the topic of electronics, I'd actually like to talk a little bit. I
Okay,
have like a
definitely.
few slides on my
Just
presentation as well.
I'll just quickly move forward. Yeah, there you go.
Yeah, yeah. So, yeah, like the chip shortage is a real problem. Like to give a short answer. Oh, sorry. Before that, so I have a picture of our Aether satellite, and so from a 2U tiny satellite, I went to working on 6U satellites, and in between the lunar lander and now this. So this is going to be a 100 kg class satellite. Has most of the subsystems that I spoke about earlier as well. The EPS, for instance, the attitude and orbit control equipment, the avionics bay. But let me skip through that. And uh, sorry, yeah. So electronics for space. So first, let me answer the question that you had asked bluntly. So it has really like affected us greatly. Like now, supply chains are like terrible. Like there are certain chips for which the wait is like more than a year and a half, 2 years, and we are having to redesign a lot of our legacy systems just because parts are not available. And any new designs that we are doing, we have to first think about it from a supply chain point of view, make sure we have enough stock available, and only then proceed with that. Uh, so back to electronics for space, like one of the most important things is reliability, and this is where the approach of old space versus new space differs a little bit. Back in the day, you would have one satellite designed for 15 years that would cover a vast area, providing services to a vast area and it would be a geostationary satellite. Now people are launching many more small satellites to accomplish the same task. So even if one of those satellites fail, you have redundancy not on a subsystem level but on a whole spacecraft level, because these satellites are so much cheaper to launch and maintain. And that has helped us, trying to move away from really expensive rad hard by design components and start using a lot of so-called radiation tolerant components, and do other make other trade-offs and FDIR decisions. So FDIR stands for fault detection, isolation, and recovery. So if you have a fault, are you able to detect it? And if you're able to detect it, are you able to isolate it such that it doesn't cascade further? And then once you have done that, are you able to recover from that fault? So one example of this would be to counter bit flips. You could have the same sort of file stored in multiple locations, and then you could read through all of those locations periodically to make sure that all of those three locations are in sync. And if they are not, then you can do some sort of a majority voting. Like if two of the three match, then you think whatever the two of them are saying, whatever the majority is saying is correct, and go ahead with that decision. So that's uh, one way of dealing with faults in space. And in new space, a lot of trade-offs also have to be done. Like one of something that comes to my mind uh, is about batteries. Like, if you want to create a battery pack, either you can get like really closely matched cells and uh, spend a lot of money on selecting your cells to create a battery pack from cells that are very closely matched in their characteristics and who will age uh, very similarly. Or now with the advent of electric vehicles, you have battery management systems that do cell balancing. That has become very commonplace. So now we can take that commercial technology and take it to space, and like use cheaper cells to still achieve similar performance with slightly more complicated electronics. So these are some of the thoughts that uh, we think about while designing electronics for space.
All right. Well, thank you so much for answering all the questions and about the semiconductor chips and how greatly it has affected the space industry. And we have almost come to the end of this entire session. So, before we conclude with the session, what is your general advice to the participants of the Space Science Challenge 2022?
My only advice would be, if the task seems daunting, don't get scared, and just think on the from the first principles, and like try to break it down, the larger problem, into smaller, more solvable chunks, and like have fun while you do it.
It's definitely fun. That's exactly important. And before we wrap up with the session, any book or movie which inspires you the most to pursue your dreams?
Oh, yeah. So as far as movies go, like Apollo 13 was a great movie. I had read Dr. Feynman's autobiography before that, and it was great to see him. Also, great to see how astronauts and people on the ground cooperated to make it work, make things work. And no, sorry, I think I'm mixing up two movies at this point. uh, but the other recently, what I really loved was Rocket Boys, which talks about Vikram Sarabhai and Homi Bhabha. That was great. As far as books, I think Dr. Kalam's books have had some impact in like igniting a spark in me at an earlier at a younger age. And more recently, I read this book called "From the Red Planet," from a fishing hamlet to the Red Planet, which is written by, I think, which has like a compilation of many different articles about ISRO, and sort of gives a history of ISRO. So it has articles written by even by Vikram Sarabhai and Jacques Blemond, who is like a French scientist who was involved in the initial phases of uh, starting the rocket program in India, and like when they were still doing sounding rockets, and all the way to B and Suresh talking about how the PSLV GSLV was developed. And so that gives a very good
All right, I think, yeah, all right. I think there is some internet issues on Mr. Adish's end. Yeah, I think there are some internet issues on the side of Adish. It's fine, no worries about that. And well, that is, or we have almost come to the end of today's session. And well, thank you so much, guys, for joining in for today's session. Well, the next session which you'll be having is with Mr. Narayan Prasad. Um, that is tomorrow. You'll be getting, and you'll get the reminders on your email and also on the WhatsApp groups as well. We'll go ahead and yeah, we'll communicate that to you guys. So looking forward to the next session with Dr. Narayan Prasad. It's on tomorrow, that is 2nd of July at 6 p.m. Indian Standard Time. So don't forget to tune in, and also I'll just drop in the link in the chat session as well for that. And I believe that Mr. Adish has joined us back, so let me just put him back
Laptop
to the screen.
died. It just
Yeah.
got frozen, so I thought I'll join from my phone.
Yeah, no worries about that. It's completely fine. So we were almost towards the end of the session as well. Any last comments from your end? Oh, all right. No worries about that. I think there are some other. I think there are some internet issues in Mr. Adish's, and no worries about that. So as I was saying, that tomorrow we'll be having another session with Dr. Narayan Prasad. That is at 6 p.m. Indian Standard Time. Let me just quickly go ahead and drop the YouTube link in the chat section. There you go. That is what you have to tune in for the next session. That is tomorrow at 6 p.m. Indian Standard Time. And yep, I think that would be it. I hope you guys had fun in today's session meeting with Mr. Adheesh Boratkar. And there were a few questions which were left behind. No worries about that. We can migrate them to the next session as well. And I believe that Mr. Adheesh Boratkar has joined us back again. So let me just quickly pull him back to the screen. And all right, I think you're back on the screen.
Yeah, no, really sorry for the connectivity issues today. But yeah, no, I mean, very excited to see what participants come up with for this challenge. And uh, congratulations to everyone who's participating in this, and even to you for organizing this. I think, and like, thank you so much for giving me this opportunity to share my uh, thoughts with you all.
Thank you so much for connecting, or thank you so much for joining in for the session. And if you guys want to interact with Mr. Adish live, I mean, you're qualified to the grand finale and you'll meet him live as well. All right, then, guys. So, till then, ciao, everyone. Take care. Ciao, and good night, good evening, slash good day, forward, whatever time zone you are in. All right, then. Bye bye, everyone. Take care.